Hello guys, welcome back. This is a physics video lesson number 3. In this lesson, we're going to continue the energy resources. Particularly in this lesson, we're going to cover thermal power station working principle. Um, as you know, we use electricity, and most of the electricity is generated in thermal power stations. So we're going to talk about their working principle. We're going to compare a little bit, we review the energy resources, like factors. What factors we should think about it when we want to build power plant, when we want to build a nuclear power plant, when we want to build infrastructure for geothermal energy. We should compare the factors, affecting the properties we should compare. So we're going to talk about that, comparing energy resources, and I'm going to talk about the how yes, fusion in sun, how the energy is made, created, produced in sun, and scientists right now like learning from that and copying and trying to make small sun fusion on our Earth to produce unlimited a renewable and like energy resource which will not contribute to the global warming. We will talk about it in this lecture. And there will be homework, which is past paper questions, and it will be distributed through Google Classroom. There's the keywords. We're going to learn about these keywords: boiler, turbine, generator, nuclear fusion, and water cycle, plasma. Yeah, some of them. Let's carry on then. Okay. So as we talked about, the most of the electricity, most of the fuels used in power plants to make electricity is fossil fuels, isn't it? This is Taiwan. In Taiwan, as you can see, oil and coal is mostly used. They're just similar to like whole world. 85% of I mean, the electricity is produced from 85 from fossil fuels. 85 85% of the electricity is produced from fossil fuels. There is next comes nuclear in Taiwan, which is in fourth place. Wind, solar, renewables is maybe about 5%, less than 10% right now. But Taiwan is moving in the direction of to increase renewable energy resources, and even the thermal power stations will be a transition to like natural gas power stations. Okay, we will talk about it later. Right, let's talk about the um, thermal power station. So thermal power station, how it works. Um, so I need to record the time. Okay. So thermal power stations, well, there are main compartments, which is boiler, turbine, and generator. These are usually the same for most of the power stations. Just the fuel is changed, isn't it? Just fuel is changed. The fuel can be fossil fuel or nuclear radioactive elements like uranium, thorium. Uh, but the main compartments like a turbine, like boiler, where you heat the water, form the steam, and then steam is turns the turbine with the blades, and then the blades and turbine is connected to the generator, and when the generator turns, they create electromagnetism, and electromagnetism induces or drives electric current around conductor. So we will learn about these electric generators in coming chapters. But the boiler, turbine, and generator are the same for all power plants. The fuel changes, fuel can be coal, natural gas, oil, or nuclear radioactive elements. And well, now from these slides, as you have some idea about what is boiler, turbine, generator. Again, generator is can be both way. Uh, from batteries, you can use like electric motors other way to turn your wheels in your electric scooter or electric car. So it can be both. It can be used at both ways, the generator or electric motor. It can be generator if you make electricity. It can be electric motor if you use or already created or stored electricity to turn to turn it to mechanical energy and to kinetic energy, basically to drive electric car or ride electric scooter. Okay, next will be now so I said that there are when we want to build infrastructure for electricity production, like power plant, hydroelectric, or any other kind of windmills, we should consider the factors, what kind of properties affect, uh, you know, so some of the factors is, renewability. We should consider renewability, cost, availability, reliability. How is it possible to scale, and environmental impact? So, for example, renewability is important. The solar panels, solar cells, or wind turbines, uh, especially the solar cells, when they are, produced, when at the beginning you need to make some, you know, a there are some CO2 production involved when you're making this stuff. But once it is installed, it is, no fuel is required. Sun energy is free, so it can be quite effective. I mean, cheap, especially costly. For example, initial cost can be high. For example, the renewable solar panels, solar cells, as well as like geothermal, hydroelectric. But the operational costs can be very low. Because, for example, solar cells, as I said, fuel is not required. Hydroelectric fuel is not required. Availability, yes, it's important. You should consider reliability. Reliability is a, for example, uh, is it reliable? Will it work? It will not. mm, you know, there are other factors like the trade disputes, the geopolitical, the relations between countries. You should think about it. All should be considered. Scalability. Can you scale it? Can you increase the the production of energy? For example, the fossil fuel power station can be compact, isn't it, and can produce lots of energy. Still can supply a large population. Our our main goal should be increase the efficiency, isn't it? We want to get more efficient and pollute less. So environmental impact, that's the next one. So pollute less. The use of fossil fuels is climate change, isn't it? So we want to get, we don't want to pollute, we don't want to contribute to greenhouse effects. We don't want to pollute air and some other, some other environmental effects. For example, hydroelectric can flood, or dams like tidal barriers can flood. Um, so farms, other landscape. We should think about that. Right. Next would be, so next is not, it's about topic. So I said we're going to talk about how energy, you know how ener how energy is made on the sun. But before that, we're going to talk about this is again a review. The most of the energy that we use, this can be traced back to the sun. Even fossil fuels, isn't it? Fossil fuels stores of energy that came from the sun, stored on plants and decayed, so which took millions of years. The radiation from the sun can be absorbed in solar panels, isn't it? And can be uh, absorbed again by the solar cells to generate electricity. And the wind again, uh, caused by when air is heated by the sun. Warm air rises, cool air, uh, they they replace and they exchange with cool air and replace it, and that movement generates a wind. And that the air, as I talked about, the kinetic energy on the air turns turbines, and turbines generate electricity. Okay, the hydroelectric power also can be traced back to the sun. The water evaporates from oceans, lakes, seas, lakes. They go to the high surface, atmosphere, eventually cools down, form clouds, and cools down, then falls back to the earth as a rainfall. And this cycle repeats. Rains, rain goes, on the river, lake, seas back, goes also underground, and this cycle repeats, and that's called water cycle. Water cycle. Without energy from sun, it wouldn't. There would be no water cycle and no hydroelectric power. Yeah, this is it would be. And I say most of the energy can be traced back to the sun. Well, some of the energy is not from the sun. For example, tidal, nuclear, geothermal. As you know, the tidal is because of attraction, gravitational attraction from the moon. The moon attracts the surface, the oceans, lakes of the surface of Earth, isn't it? Earth and moon, they both attract each other, but there is no sea on the moon. Vice versa, moon attracts the Earth with the same gravitational force, and that gravitational force pulls the makes tides, and these are some of the on the slide. There are pictures of some of the tidal power plants. I'm not mistaken, the first one is from Canada. Second was nuclear power plant, again, not from the sun. I think it's in maybe Taiwan. Geothermal energy, Iceland, definitely. Specific, location specific, again, the origin is from Earth, or Earth's core, Earth, or Earth's crest, which is still very hot. Right. So these are not from the sun. And now let's talk about the how energy is, how energy is created, how nuclear fusion happens on our sun's surface. Okay, this is a different reaction, isn't it? This is not like power plant, as we know. There is no oxygen on the surface of sun, so there is no. I mean, there is a fuel, but there is no fuel like oil or gas, because oxygen is required to burn them. So even here it says on the slide that it releases vast amount of energy, but it is not burning fuel, isn't it? Same way as we do in our power plants. It is not chemical reaction. It is not chemical reaction. The sun consists largely of hydrogen, but there is no oxygen to burn this gas. Instead, energy released in the sun by the process of nuclear fusion. Okay, what's nuclear fusion then? Well, it is a joining of two nuclei, which is proton and neutrons, no electrons, there's no electrons, nuclei of two atoms uh, to form a single and more heavier atom. And in the surface of the sun, it is hydrogen. Two hydrogen nuclei is fused or joined together to form a helium. And this process requires extremely hot environment as well as high pressure, which we cannot. That's why it's very difficult to make these conditions on our Earth. Otherwise, we could have, made some reactor just like the sun, small sun, and get unlimited of energy from that. But still, this research is going on. I'll talk about it next slide. So for the fusion to occur, the electrostatic repulsion between the atoms must be overcome. Creating these conditions is one of the major problems in triggering a fusion reaction, which requires maybe hundred million degrees Celsius temperature and very high pressure. So right now the research going on. So this is a reactor which will copy what's going on the sun, on the surface of the sun, which is fusion. There is tokamak. This nuclear reactor called tokamak. It's like a donut-shaped reactor. So what's going on here? Well, as just like on the surface of the sun, the protons, the protons of lighter atoms are collided and form heavier atom, which is helium. So when they collide, they release heat in the form of light as well as protons. They release extra protons. In the previous slide, I think there is an animation here. So here, for example, in this back screen, there is a fusion going on and one proton is released. I'm sorry, the neutron or other particles is released, and that released particle has got the energy. heat energy, as well as light released. So we want to harness light as well as release particles energy. It is about whether it is neutron or proton. We want to use that energy which that particle carries. And so in this tokamak, there is a plasma, which is, plasma is ionized gas. It is like freely moving protons, neutrons, and electrons. Like soup of freely moving ions. Uh, Basically, plasma is like fourth, uh, how do you put it? Fourth state of matter. Yeah, there is a solid, a liquid. There is a solid. When you heat the liquid, it becomes a solid. When you heat the solid, it becomes a liquid. When you heat the liquid, it becomes a gas, like ice, water, vapor, or steam. Once you keep heating the steam, uh, the gas molecules, the water molecules, gas in the what form of gas, bumping, hitting each other, filling in this container. The electrons around the hydrogen oxygen atoms, if you heat them so high, which requires very extreme conditions, the electrons around them will be released because they gain so much energy. They will go out of their orbitals, and that in that case they will ionize, and that's called plasma. Well, as plasma is very complex for state of matter, it is still research is going on, and there's plasma researchers, plasma physicists. So still very complex, still research going on, but the basic idea is this. This is a soup of ions freely moving around. They have so much energy. By the way, plasma is used in disinfection, as I remember, even welding. When you weld, you use to melt the metal. You use plasma. There is plasma. We can see plasma on the lightnings, high energy. Because of this high energy, they create plasma. All right, so some of the examples in plasma. On universe, a lot of matter is in a form of plasma in the universe, but on Earth it is not. Happens on Earth it's not. That's okay. Okay. So next is comprehension check. What's plasma? Yeah, please pause the video and you can research. If you don't understand my speech, please research, read about it, try to understand what's plasma, and compare how plasma confined in a star with how we will achieve some effect here on Earth. So how plasma is on Sun, or how on the surface of Sun. By the way, the surface of Sun is a plasma, high energy gas. Yeah, ions flowing around. And how it is confined, and how can we create same effect on Earth. And discuss advantages of nuclear fusion. So we should know about nuclear fusion and we should discuss it. Please think about it. And what's the difference between nuclear fusion and nuclear fission? Fission and fusion. Okay. Yeah. Pause the video, do research, learn about it. Alright. Okay. So, I'm back. I just checked the time. I think I think I can record this video in whole. This video can be only one video, no need to divide into two parts. Okay, let's continue. So to summarize our chapter, the solar panels are used to collect energy from the sun. Solar panels, furthermore, can be improved by you putting solar cells. If you put solar cells on the solar panels, you can directly generate electricity. The solar panel is also used to heat the water, and further, if you develop it for the put on the solar panel a solar cell, you can make a photovoltaic cell where you can generate electricity. Oil, coal, and natural gas are all examples of fossil fuel. Coal forms from trees, oil and natural gas from microplanktons. Coal took maybe 250, 300 million years. Oil and natural gas took about 100 million. So non-renewable energy resource will run out. That's why we need to transition. We should transition to renewable energy resources. This includes fossil fuels and nuclear fuel, but not biofuel. So fossil fuel and nuclear fuel are non-renewable energy resources. But biofuel is a renewable energy resource. Why? Well, biofuel can be generated in a short time. It won't run out. It will not deplenish. It can be replaced or renewed in a short time. The biofuel. Right. Renewable energy resources are replenished, replaced after they have been used. That is the summary. Biofuels are renewable, reliable, cheap to set up and use, but they are diffuse. They are, how can I say, not condensed energy resource. Diffuse. And can be also said dilute. Diffuse and dilute. So I checked the meaning. So diffuse means, or dilute means, they are not very reliable. When you want them, they're not always there. Efficiency is very low. Not available constantly. Dilute meaning of dilute or dilute meaning of diffuse is they are not available constantly, and their efficiency is very low. Efficiency is low. So these are the meanings of dilute and diffuse. Okay, I think the summary 2. Let's continue. So geothermal energy is harvested, collected where hot rock is close to the Earth's surface, and hot rock is close nearby. Yeah, like volcanoes or mountains. Wind power, wave power, and solar power are renewable but unreliable dilute energy resources. Again, dilute means they are not available constantly, and the efficiency could be low. For example, solar power efficiency, solar cell, photovoltaic cell efficiency right now. What do you think? Please research about what's the efficiency of average solar power. It should be about 20-25%. So not very efficient. Okay. Running costs are low. Okay, the running costs are low. The initial. So sorry guys, I have to make it in two parts of video, in two parts. So I'm going to pause it here. This will be part 1. I'll see you in part 2.